Today's topic, inverse trig functions. And if you remember, we had 6 different trig functions. We had sine, cosine, tangent, cosecant, secant, and cotangent. But really, today, at least, talking about the inverse trig functions, I'm only going to talk about 3 of them: the inverse sine, inverse cosine, and inverse tangent. Those are really the most important. And even more so, I will say, when you move into Calculus 2, you will see mostly inverse sine and inverse tangent. Okay, well, this is a graph of f of x equals sine x. We know the domain is minus infinity to infinity. It's natural domain. And it ranges between -1 and 1. This function's periodic with period 2 pi, and it goes 0 high, 0 low, 0. Okay, well, if you think back to our inverse function theorem day, you might be thinking, wait a minute, there's not an inverse function for sine if you just stare at this graph, because, let me put this as a bullet, this function on its natural domain fails the horizontal line test. Okay, so this function is not 1, 2, 1. In fact, any horizontal line between -1 and 1 will hit this graph infinitely many times. Okay, but the title, inverse trig functions, okay? The story is not over. What we do, if you have a function like the sine that fails the horizontal line test on its natural domain, we may restrict the domain in a way that makes the function 1, 2, 1. Okay, so maybe I'll use blue here. We restrict the domain to minus pi over 2 to pi over 2. Now, when we do this, it's just this piece, minus pi over 2, and then it comes up here, all the way up to here, okay? And then f of x equals sine x on this restricted domain. This passes the horizontal line test. This is 1, 2, 1. And the image, or the range, is -1 to 1. We fill out the entire range of the sine just by looking between minus pi over 2 and pi over 2. And so we have an inverse function. F inverse of x is the sine inverse of x. And this maps, or this has domain -1 to 1 and range minus pi over 2 to pi over 2. And so our text typically uses this sine to the -1 notation, but other notation, and you might hear me refer to this some this semester, is arctan. Okay. Now we see this restricted domain. So this, let me add this. This is on minus pi over 2 to pi over 2. Okay, so just as I was discussing the inverse function, I'll write it here. This maps -1 to 1 onto minus pi over 2 to pi over 2. Now, this is an important thing to keep in mind. What is this function? Sine inverse of x. Well, first of all, x needs to be between minus 1 and 1. Okay, we see it here. But this is an angle, so I'll write this as a theta. This is sine inverse gives you back an angle. I'll say if and only if sine of theta is x and let's say theta is between minus pi over 2 and pi over 2. So this function, the inverse sine, it takes in a sine value and it gives off an angle, okay? And if I want to match, okay, wonderful, I can just change this so we also see the variable theta here. It's fine. Okay, let's do a few examples here where we just think about evaluating the sine inverse. Okay, so this says the sine is 0 and theta is between minus pi over 2 and pi over 2. What's theta? Well, we're looking at a graph and we know the sine is 0 at 0. Okay, this says the sine is minus 1. Okay, and theta is between minus pi over 2 and pi over 2. Okay, here we go. Theta is negative pi over 2. So far, so good. This one says the sine is square root 2 over 2. And theta is between minus pi over 2 and pi over 2. Okay, this is pi over 4. And finally, the sine is negative a half. And theta is between minus pi over 2 and pi over 2. Well, let's see. This one I might have to think. Sine is a half. Reference angle would be pi over 6. But it's negative, so we get negative pi over 6. Okay. Now, one more thing to say, and then we will move into derivatives. Let's start with a number between minus 1 and 1. If we first take sine inverse of x, and then we take the sine inverse of x, this is a number between minus 1 and 1, then sine inverse gives you an angle. Okay, then you take the sine of that angle, well, we get back to x. Okay, now on the other hand, so this holds, okay, on the domain of sine inverse. On the other hand, first if we take the sine of theta and then take sine inverse, this is not necessarily equal to theta if you take theta to be on sine's natural domain. So this is not something that holds in general. And a quick example to see that is, for instance, if we take sine inverse of sine of, let's say, 5 pi. Well, sine of 5 pi is 0, so this would be sine inverse of 0, but sine inverse of 0 is 0, which is not equal to 5 pi, okay? Certainly, if you start with a theta in this restricted domain, minus pi over 2 to pi over 2, this second equation would hold, but this does not hold generally on the natural domain of sine, okay? So I would just be careful about that. Well, now if we get into derivatives, the derivative of the inverse sine is 1 over square root 1 minus x squared. And I should add, this is 4x in this open interval. Certainly, what I have written as the derivative is only defined here. So the domain, natural domain of this function is open -1 to 1, but also, and we have discussed this, that a function whose domain is a closed interval, as is the case with the inverse sine, it's not going to be differentiable on the endpoints. Okay, now, how do we see this? We may use the inverse function theorem. Well, f of x equals the sine of x on, I'll do this, open, pi over 2 to pi over 2. Okay, this satisfies f prime of x is the cosine. And on minus pi over 2 to pi over 2, if you think about the cosine, here's minus pi over 2, here's pi over 2. The cosine is positive. So this is strictly positive, and in particular, not equal to 0 on this open interval. Okay, so this means we have a function on an open interval. Its derivative is not equal to 0 on the open interval. This means we may use inverse function theorem. Oh, I already have it above. Use inverse function theorem. Maybe I won't write it again. This says that f inverse prime at some b equals 1 over f prime of f inverse of b. Now, we are going to have to unravel this. Let me take one more step. We know f prime of x is the cosine. F inverse is the sine inverse. And this is for b in. It would be the image of this open set, which is -1 to 1. Now, we don't want to leave this as a formula for the derivative. This is not very helpful. So we want to get ourselves to this, which here I have a b. What I want is a 1 over square root 1 minus b squared. So let's unravel this a little bit. What does this say? It says, okay, if the sine of theta is b and minus pi over 2 less than, well, strictly less than theta less than pi over 2, what is cosine theta? This is exactly whatever this is. Okay, if you have sine value equal to b and you're sitting between pi over 2 and minus pi over 2 and pi over 2 open, what is the cosine? Okay, well, we can get this out of the sine value b because we know, let's see, we know this is this most important identity I have mentioned about trig functions, that sine squared plus cosine squared is 1. And this gives us b squared is plus cosine squared is 1, or cosine squared theta is 1 minus b squared. We get cosine theta is the square root 1 minus b squared. And it's the positive square root because theta is between minus pi over 2 and pi over 2. And cosine is positive. Okay. So this quantity in my denominator is square root 1 minus b squared. So all together, now this was kind of my side work commenting, but we see this 1 over cosine f inverse prime of b is 1 over square root 1 minus b squared, okay? Which is exactly this formula here, okay? This was inverse function theorem. Now for the cosine and inverse cosine. Here is a graph of cosine x, periodic with period 2 pi, ranges between -1 and 1, and the cosine goes high, 0, low, 0, high. And in green, just as we had for sine, if you consider cosine on its natural domain, -infinity to infinity, it fails the horizontal line test. Okay, now, we can't just do the same restriction because -pi/2 to pi/2, this was the restricted domain for the sine, you see here, still fails the horizontal line test. So typically, for the cosine, we restrict the domain to 0 to pi. And here, on this closed interval, cosine restricted to the interval 0 to pi, this is a 1-to-1 function. Okay. Then f of x equals cosine x has an inverse function, which is cosine inverse of x, or it's the arc cosine. This is other notation. And it's very similar to the inverse sine, where this takes in a number between -1 and 1. So here, this domain, -1 to 1, and the range 0 to pi, okay? So the inverse cosine takes in a number between -1 and 1. It's a value of a cosine, and it gives you back an angle. That is between 0 and pi, okay? So just as a quick example, let's say we want the cosine inverse of -1/2. I think we did sine inverse of -1/2. Well, here's cosine inverse of -1/2. Okay, this says we're between 0 and pi. Here, 0 and pi. So we're somewhere up here, and the cosine is -1/2. Well, you will be in quadrant 2 because the cosine's negative. And the reference angle, cosine is 1/2 at pi/3. So the reference angle is pi/3. It would be pi minus pi/3, or 2 pi/3. Okay? One more example. Let's do the cosine inverse of the sine of, let's say, 3 pi/2. Okay? Well, first we need to figure out the sine here. 3 pi/2 is here. Sine of 3 pi/2 is -1. Okay? And then cosine inverse of -1, we want the angle up here between 0 and pi such that the cosine is -1, and it is out here at pi. Okay, so those are just two examples, just using these inverse trig functions. And now let me, in this box down here, I'll mention the derivative. The derivative of the cosine inverse of x. This is -1 over square root 1 minus x squared. Okay? So it's almost like the derivative of sine inverse, except with a minus sign. If you wanted to justify this or realize this calculation, you could proceed just as we did for the inverse sine function, using the inverse function theorem, okay? I'll leave that as an exercise. Well, here are two examples to find the derivative. Here we have 2 to the sine inverse of x. This is a chain rule. Inside function is the inverse sine, and the outside function is 2 to the x. Y prime is, well, the derivative of the outside, which is here, and then evaluate it at the inside, okay? And then times the derivative of the inside function. Derivative of the inverse sine is 1 over square root 1 minus x squared. We could put parentheses here if we wanted to. Okay, so this is y prime. Now, this is another composition, chain rule. My inside function is cosine inverse and the outside function is the sine. Y prime is derivative of sine is cosine, evaluated at the inside function, and then times, well, I just mentioned the derivative of the inside function is minus 1 over square root 1 minus x squared. Now, this is a great example because we have cosine of cosine inverse, and I didn't explicitly write this, what this is, but I did for the sine. You see, you start off with a cosine value, then you figure out the angle. This is cosine inverse. Okay, so now I have an angle, and then I ask the cosine of that angle. This here is just x. This is x for every x in the domain of the cosine inverse. Okay, so this simplifies significantly. Y prime is minus x over square root 1 minus x squared. Okay? Oh, I meant to write this is just x. Okay. Well, let's do another example or two, and then we will talk about the inverse tangent. Two more. Here, what do we see fundamentally here? We see a product rule. Here is first times second. So y prime is the first times, I'll do this one in 2 steps, derivative of the second plus the second times derivative of the first. Now here, cosine inverse of 1 over x, to differentiate this is a chain rule. My inside function is 1 over x, or x to the minus 1, and the outside function is the inverse cosine. Okay, so we have derivative of the outside. Ooh. Evaluated at the inside. Okay, so this is derivative of the outside, evaluated at the inside, and then times derivative of the inside function. Okay, and then this is just cosine inverse of 1 over x. Now, this is something we can definitely simplify. I have 2 negatives. This first term is positive. I have an x over x squared, which is just 1 over x. I'll just leave it like this though, okay? Because I see my work and I didn't need to simplify the derivative anyways. Okay, now for this one. Well, this was product. This one is quotient. We have denominator times derivative of the numerator. Derivative of e to the x is e to the x. And then minus the numerator times. Now I differentiate the denominator. Okay, 1 over. Okay, it's a chain rule. There's derivative at the outside. Evaluated at the inside will be a 2x here. And then times derivative of the inside function. Inside function has derivative 2. And then all over denominator squared. Okay? Perfectly fine, just like this. Now I did this one on purpose so that I can make an important comment. Okay. So I'll write this as a note. The sine inverse, I'll just write it in terms of x, okay, is not equal to 1 over the sine of x. Without a doubt, it is not. I think this is why some people don't like this notation and why they like the arcsine notation better, because this minus 1 means inverse function. It does not mean 1 over. But because of this, it is definitely follows that if you have sine inverse of x squared, this is not equal to, okay, definitely not. This would mean 1 over sine squared of x, and that is not what this means. So this denominator here, okay, it has a 2x. You cannot say this is sine of 2x to the minus 2. It doesn't work like that. So this is how we need to leave this, okay? Don't try to simplify it using some property of exponents that does not apply here. Now comes tangent and the inverse tangent function. Well, my graph is certainly lacking in accuracy. Well, it's a sketch. And you notice I don't have any Y tick marks. But this is the basic shape of the tangent. We know f of x is sine x over cosine x. And so this function is undefined everywhere. The cosine is 0 because you can't divide by 0. And cosine is 0 at pi over 2, say plus integer multiples of pi. So pi over 2, 3 pi over 2, minus pi over 2, minus 3 pi over 2, like this. If we draw the unit circle, it's here and here. Okay, we need to keep going around all of those places. The cosine is 0, and so the tangent is undefined. And this is the basic idea. Now, just like sine and cosine, this graph on its natural domain fails the horizontal line test, okay? So with the tangent, we want to restrict the domain of f of x is tangent of x to, open, minus pi over 2 to pi over 2. So in effect, in order to define the inverse tangent function, we are looking at this part of the tangent. Okay? And when we do this, we get a one-to-one function. Then the range of the tangent is all real numbers. This is one reason why the tan inverse is so beautiful, because f inverse of x, which is the inverse tangent or the arctan, this has domain. Well, the domain is the range of the tangent restricted to minus pi over 2 to pi over 2, and that is minus infinity to infinity. So this is the domain of the inverse tangent. And range open to pi over 2. This is the only one that we have discussed today where the domain of the inverse trig function is minus infinity to infinity. This is one reason why the inverse tangent function is so beautiful, because it's defined for all real numbers, okay? And again, x will be a tangent value, and tan inverse of x hands you back an angle that has that tangent. Okay, now, before I get into derivatives, I want to make some observations about limits here. I have changed this again to be theta because I'm going to go back and forth between the tangent and inverse tangent, and I have just graphed it on its restricted domain. So now let's discuss limits. As I was saying, we know the limit as theta goes to pi over 2 on, let's see, coming in from the left of the tangent theta is infinity. And the limit as theta goes to minus pi over 2 on this side of the tangent theta is minus infinity. Okay, now let's translate this into a statement about the tan inverse. Okay, the limit as, let's say, x approaches infinity of the tan inverse of x is pi over 2. And the limit as x approaches infinity, minus infinity of the tan inverse of x is negative pi over 2. And let me just, we know what the graph would be. Let me talk about it, then I'll sketch it. To get the graph of the inverse tangent, which as I mentioned, defined on the whole real line, and we can calculate the limits at infinity by looking at limits for the tangent. But the way we get the graph is you take this one, and then there's a line y equals x, which goes through here, and you flip about the line y equals x. Okay, so try to visualize this, flipping this about the line y equals x. Try to visualize it now, because I'm about to draw it for you. This is the inverse tangent. I hope this is what you were thinking about when I asked you to envision it. We took the tangent, okay? And then we reflect it or flip it about the line y equals x. Interchange x and y, and this is the inverse function. But the reason I like graphing this inverse function the most out of all of the trig is because, as I mentioned, this is defined on the whole real line. And we can take a limit as x goes to infinity of the tan inverse, pi over 2. A limit as x goes to minus infinity of the tan inverse is minus pi over 2. And both of these come up in, I'd say they come up a bunch in calculus 2, but we're also seeing them now, calculus 1. Let's work with inverse function theorem again. Okay, so we know f prime of x is secant squared x. Now again, just like when we were working with the sine, the open interval here is minus pi over 2 to pi over 2. Secant squared, it's always positive. So it's never 0 on this open interval. Okay? The secant is always positive, so certainly secant squared is, but in particular it's never 0. Okay, so then we may use inverse function theorem. And what do we get? We get that f inverse prime, this is the derivative of the inverse tangent at some b, is 1 over f prime of f inverse of b. And this would be for b in the image of the tangent, which is minus infinity to infinity. It's the domain of the inverse tangent. Now, just as we did with the sine, we were working with the inverse sine, let's fill in what these are. We get f prime is secant squared of, and then f inverse is tan inverse. Okay, now, yet again, we don't want to leave it like this. This is not that informative. But what can we do this time is very similar. So let me come over here. We know sine squared plus cosine squared is 1. Now, let's divide by cosine squared. If we divide this entire equation by cosine squared, we get sine squared over cosine squared, which is tangent squared. We get cosine squared over cosine squared, which is 1, and we get 1 over cosine squared, which is secant squared. So this is another identity, trig identity. And it follows directly from this one. Let me change these two. Okay, I just changed those to theta. What this says is the tangent of theta is b. What's secant squared? Right? Okay, well, the tangent of theta is b. We see it immediately. Secant squared is b squared plus 1. Oh, I kept my lighter blue here, but it's fine. Okay, so here we see f inverse prime at b is 1 over 1 plus b squared, and this is exactly justifies that, I'll write it this way, the derivative of tan inverse of x is 1 over 1 plus x squared. Okay, it was inverse function theorem yet again. Here are two derivatives that involve tan inverse, quotient rule, and product rule. Okay, here we have log base 3 divided by tan inverse of x plus 8. Y prime, we take denominator times derivative of the numerator, and this would be 1 over ln 3 times 1 over x minus the numerator times derivative of the denominator, and then all over the denominator squared. Okay, and finally this one, product rule, we have first times derivative of the second. This one is the chain rule. Derivative of the outside evaluated at the inside, and then times derivative of the inside function. First derivative of the second, and then plus the second times, well, the derivative of secant was secant tangent. So we have secant x, tangent x. Okay? So here are these two derivatives. This will be my last example. We want to find inflection points for the inverse tangent. And we know inflection points are where the graph switches concavity, goes from concave up to concave down, or concave down to concave up. And how you tell that through calculus is using the second derivative. Okay, well, the first derivative is 1 over 1 plus x squared, which, let me write it this way because I'll differentiate again. So the only reason I'm calculating first derivative here is to get myself to the second derivative. And here is what I'm interested in, second derivative. This is a chain rule. Okay, but you see, possible inflection points where the second derivative is 0 or does not exist. So let me write this in a way we can more easily set it to 0, would be like this. Okay, if we look at this second derivative, this is defined everywhere. So the only possible places we may have inflection points are where the second derivative is 0. A fraction is 0 only when the numerator is. And so let's check. Now you can't just conclude x equals 0 is an inflection point, not with the work we have so far. There is something to verify, okay? My intervals would be like this. If I needed, for example, intervals of concave up and concave down, and then I pick a point in each interval and test the second derivative because this has to do with concavity. Okay, so what I want is the second derivative. Okay, so I have x. My second derivative is minus 2x over 1 plus x squared squared. Well, all I'm evaluating it is minus 1 and 1. The denominator is always positive. Evaluate this at minus 1, we get a plus. Evaluate this at 1, we get a minus. That was not too terribly hard. So we have, okay, the graph of tan inverse is concave up to x equals 0. Then it switches to concave down. So we can conclude we have an inflection point at x equals 0. And similarly, if you wanted to put the point on the graph, the point on the graph, just as a comment, is 0, 0, because the tangent of 0 is 0, which says that the tan inverse of 0, well, is 0 also. Okay, but this is the x value. We have an inflection point at x equals 0.